In the summer of 1946, a president signed a law that fit on a few pages. No ship was launched that day. No gun was fired. Most Americans never heard about it, and the ones who did forgot by the weekend. That law quietly built the most dangerous navy the world has ever seen. Here is the strange part. The thing that made America unbeatable at sea was not a battleship. It was not a submarine. It was not some secret weapon hidden under the ocean. It was an office. A building full of scientists, contracts, and phone numbers for professors. By the end of that same year, that office was already paying for more than 400 research projects. The bill came to over $22 million, which was a fortune in 1946, and almost none of it went to weapons anyone could see. This is the story of how America stopped chasing single inventions and built a machine that makes them on purpose. A machine that turns science into sea power, over and over, for 80 years. When you understand how it works, you understand why no other navy on Earth has managed to catch up. To see why this mattered, go back a year earlier, to the end of World War II. The war had just taught the U.S. Navy a brutal lesson. Battles at sea were no longer won by the biggest ship or the bravest crew. They were won by radar that spotted planes before the human eye could. By machines that cracked codes and did math faster than any room full of clerks. By systems that tied ships, planes, and radios into one nervous system. The Navy noticed something. Every one of those advantages came from a lab, not a shipyard. But there was a problem. When the war ended, all those brilliant scientists went home. The university teams that built the radar and the early computers packed up and returned to their classrooms. The wartime deals expired, and the Navy realized it had no way to keep those people working on the next thing. Winning the last war was not enough. Somebody had to win the war that had not started yet. Secretary of the Navy James Forrestal saw it coming first. In May of 1945, before the fighting was even over in the Pacific, he set up a temporary group called the Office of Research and Inventions. Think of it as a rough draft, a test run for something permanent. The test worked. So on August 1st, 1946, President Harry Truman signed the law that made it real. The Office of Naval Research was born. People just called it ONR. And its job was written in plain words: plan, foster, and encourage scientific research tied to future naval power and national security. Read that again. Future. Not this year. Not this weapon. The future. That single word changed everything. Most military spending works one way. A general wants a bigger gun, so the country builds a bigger gun. ONR flipped that around. It did not start with a weapon and work backward. It started with a question, funded a scientist to answer it, and waited to see where the answer led. Sometimes the answer led nowhere. Sometimes it led to something that would sit on the ocean floor and change the balance of world power for the next 50 years. And the way ONR spent its money was the strangest choice of all. It went outside the Navy. ONR sent money to universities. It sent money to private labs. It funded physicists studying strange waves. It backed engineers working on materials that could survive heat, salt, pressure, and shock. It paid mathematicians to solve problems that sounded useless at first. How does sound move through deep water? How does a metal surface scatter a radar signal? How can a machine make a choice when nobody is holding the controls? Those questions did not look like naval weapons. That was the point. A ship may take years to design and build. A new idea can take even longer. If the Navy waited until a threat appeared, then started the science, it would already be behind. ONR paid for the work before there was a crisis. It built a long line of research that ran from a college lab to a Navy ship. One end asked basic questions, the other end watched the sea. The Naval Research Laboratory was part of that line. It had existed before ONR, and it gave the Navy a place where science could meet real military problems. Researchers could test radio signals, study the upper air, work on electronics, and find out what failed under hard conditions. The ocean is hard on everything. Salt gets into wires, waves shake equipment loose. A calm sea can turn rough in minutes. Underwater, radio signals fade. Light dies fast. Sound bends, bounces, and travels in ways that can fool even a skilled operator. A lab result on dry land means very little until it works in that mess. That is why the Navy needed more than clever people. It needed a system that could take an idea through every ugly step between a notebook and a ship at sea. A university might discover a new way to read a signal. A private company might turn it into a part small enough to fit inside a machine. Navy engineers could test it. Sailors could use it, complain about it, and tell the designers what broke at 3 a.m. in bad weather. Then the work went back to the lab. That loop kept running. At first, much of the work focused on the problems World War II had made impossible to ignore. Radar was one of them. Radar gave ships and aircraft a way to detect objects beyond the horizon or through darkness. But early radar was big, rough, and limited. It had to keep getting better. The Navy wanted clearer signals, longer reach, smaller gear, systems that could tell a harmless wave from a threat. Every step changed what a fleet could do. A ship that sees first has more time. More time means more choices. It can move, warn other ships, launch aircraft, or prepare a defense. At sea, those few extra minutes can decide whether a crew sees danger coming or sees it only when it is too late. Then came computers. Early computers were huge machines. They filled rooms, they ran hot. They needed teams of people to keep them working. But the Navy saw the use right away. Modern war produces too much information for a person to sort by hand. Radar signals, radio calls, weather reports, navigation data, the speed and heading of nearby ships. The ocean does not pause while an officer studies a stack of paper. ONR-backed work helped lay the ground for the first digital systems that could handle data in real time. That phrase sounds dry. Out at sea, it meant a ship could take in fresh information and act before the moment passed. The Navy was building a brain for its fleet. And that brain needed to know where it was. Navigation had always mattered at sea. For centuries, sailors used stars, charts, clocks, and skill. Bad weather could hide the sky for days. A small error could put a ship far from where its captain believed it was. Then the Navy began helping build tools that changed that problem for good. GPS came much later, but its roots ran through this research system. Signals from satellites could tell a ship, aircraft, or vehicle where it was, with far greater accuracy than old methods allowed. A fleet could now coordinate over huge distances with shared positions and shared time. That matters even more when weapons move fast. But knowing where you are is only half the problem. The Navy also needed to know what was hiding below it. Under the water, sound is everything. Radio fades fast down there, but sound can travel for miles. So the Navy poured research into how sound moves through the sea, how it bends when the water gets colder, how it bounces off the bottom, how a faint noise from a distant engine can be pulled out of the ocean's constant hiss. This was some of the hardest science ONR ever paid for. The sea is loud. Waves, rain, fish, ships, and shifting layers of warm and cold water all mix into a wall of noise. Finding one quiet target inside that wall is like hearing a whisper in a crowded stadium. The Navy learned to hear that whisper. Better sonar meant the fleet could track submarines that thought they were invisible. It meant a ship could tell a real threat from a school of fish or a passing current. And the same research that helped find enemies also helped hide friends. If you understand exactly how sound reveals a submarine, you also understand how to make your own submarine harder to find. That idea, hiding from detection, grew into something bigger. By the 1980s, the research system had pushed into stealth. Not just for submarines, but for the shape and surface of ships and aircraft. Every hull, every angle, every coat of material could be studied for how it scattered a radar signal or reflected sound. Shave down what a sensor can detect, and you shrink the distance at which an enemy even knows you exist. A ship that is sen late is a ship that is hard to hit. Then the work turned to a question that still shapes the Navy today. Can a machine make its own choices? For most of history, every vehicle at sea needed people aboard. People to stir, people to watch, people to decide. But people get tired. People need food, air, and sleep. And every crew you send into danger is a crew you can lose. ONR-backed research helped open the door to autonomous systems. Vehicles that could move, sense, and act with little or no human hand on the controls. Some crawl along the sea floor. Some fly. Some sit on the surface for days, watching an empty stretch of ocean nobody wants to waste a crew on. Think about what that changes. A machine can wait in one spot for a week without complaint. It can go into water too dangerous for a submarine full of sailors. It can search, map, and report while the people stay safe and far away. The Navy was learning to send its eyes and ears where it once had to send its people. And the newest frontier runs on light itself. Directed energy, weapons that do not fire a shell or a missile, but a focused beam. This is some of the most demanding physics the Navy has ever chased, and it came out of the same long pipeline that started with radar and sound. Here is where the whole story clicks into place. Look back at that list: radar, computers, navigation, sonar, stealth, autonomous machines, directed energy. Every one of them arrived at a different time, from a different lab, for a different reason. No single genius invented all of it. No one weapon carried the Navy. What carried the Navy was the system that made all of it possible. The office, the contracts, the long line running from a professor's chalkboard to a ship in a storm. That is the thing rivals cannot copy by stealing one blueprint. You can steal a design. You cannot steal the pipeline that made the design and then make the next one. Other countries saw what the U.S. Navy had built and tried to catch up. Some bought the same weapons from the same companies. Some reverse-engineered captured gear. Some hired brilliant scientists and told them to match what America already deployed. But buying one weapon is not the same as building the system that invents the next 5. Think of it this way. A rival can look at a Navy ship and count its missiles. They can measure its radar range. They can study its hull shape and copy the stealth angles. What they cannot see is the decades of funded research that made every part of that ship possible. The thousands of projects that failed. The professors who chased dead ends. The labs that tested materials nobody ended up using. All of that invisible work, paid for years before the ship existed, is what made the ship work. And while a rival is copying that ship, the same system is already building what comes next. That is the gap. Not the gap between one Navy and another. The gap between having a research machine and not having one. ONR never worked alone. It sat at the center of a broader network the Navy calls the Naval Research Enterprise. That network includes the Naval Research Laboratory, the Naval Postgraduate School, warfare centers scattered across the country, and partnerships with hundreds of universities and companies. Some of those places work on weapons. Some work on materials. Some study how sailors think under pressure, or how to keep a crew healthy on a deployment that lasts months. The system feeds itself. A discovery in one lab gets tested at a warfare center. If it works, it moves to a ship. If it fails, the scientists find out why and try something else. Either way, the Navy learns. And here is the part that makes it nearly impossible to match. The system does not just solve the problems the Navy knows about, it solves problems the Navy has not thought of yet. A researcher studying fluid dynamics might stumble onto something that changes how a hull moves through water. A team working on signal processing might find a way to pull useful data out of noise, and suddenly every radar and sonar system gets sharper. A metallurgist testing heat resistance for engine parts might create a material that lets a weapon work in conditions that would melt older designs. None of those breakthroughs were ordered. They were enabled. The Navy created the conditions where discovery could happen, then stayed ready to use whatever came out. That patience is rare. Most countries fund science when they need an answer fast. The U.S. Navy has been funding science since 1946, whether it needs an answer that year or not. 80 years later, the result is a fleet that does not just fight, it adapts. When drones became a threat, the Navy already had research running on autonomous systems and directed energy. It did not start from zero. It pulled from work that had been quietly moving forward for years. When cyber warfare became real, the Navy did not have to invent the idea of networked defense. It had been thinking about connected systems since the first digital computers went to sea. When rivals began building longer-range missiles, the Navy already had research into detection, tracking, and interception running through multiple programs at once. It did not solve the problem with one crash project. It combined pieces that had been developing in parallel. That is what the system does. It gives the Navy options. And options, at sea, are survival. A ship with one way to defend itself has one chance. A ship with layered defenses, each covering the weakness of the others, has time to respond even when the first layer fails. A fleet that can see farther, move faster, hide better, and adapt quicker than the enemy does not need to be lucky. It just needs to be ready. The Office of Naval Research made ready into a profession. So when you ask how America built naval power that could destroy rivals in seconds, the answer is not one ship or one weapon. The answer is a law signed in 1946 that turned discovery into doctrine, a system that outlasted every ship it ever helped design, and a pipeline so long, so deep, and so durable that by the time a rival figures out what the U.S. Navy has today, the Navy is already building what it will have tomorrow.